Thank you for coming. Thank you for allowing us to present our company and our software here. Thank you, Mark. Oh, where is he? Oh, Mark. This is the second time I'm allowed to speak here. Last time was a big success. I think Simon Tech was there, and today I also hope you enjoy the presentation. We will do this presentation interactively, so whenever there's something wrong I'm saying, or whenever there's something you don't like what I'm saying, just shout me down and interrupt me as rude as possible. I know that's very hard for British people, but you have to keep trying. So Joe, the presentation is called router peering. Who of you has experience working with Amazon, working with VPC peering? So who in this room has set up VPC peering at least once in your life? Okay. To the others, this presentation will gonna probably be super boring. And we will make it work. As Joe said, the company Midokura, it's a company that's based in Tokyo, Barcelona, San Francisco, and Munich, and Lausanne. Dan, Mihai, Dimitri, and Tatsuya Kato built this company. Dan and Pino, who is not on this picture, were coming from Amazon. So they had a background in distributed computing. They came from Cornell. They built large-scale distributed computing systems at Amazon. For example, the DynamoDB, which powers all the market, and the shopping cart activity at Amazon was created by the team from Dan and Pino. So they have a big background in building large-scale systems. And TK, who's basically the leader of our company and the chairman and responsible for the financial aspects. And after Dan and Pino basically built this company, we hired Joe. And from then, everything became better. This presentation is split into two talks. The first talk will be a general introduction and an introduction to MeetUpNet. What is MeetUpNet? How does it work? The reason why this is important is because router peering is based on the way MeetUpNet works. MeetUpNet is a network virtualization software. That means we pretend we know what we are doing when we are doing your networking. Sometimes our users actually find out that there are some things we don't know about networking, but because it's software, it doesn't have a life cycle of several years in silicon and switches and stuff that you buy on the market. In our software, we had cases where a customer pointed out that some things were wrong, and on the next day, their software in their data center was already running the fix. And some of these customers were Joe's customers. So he can tell a lot about these cases. Did you press next? No.
I did.
Okay.
Are we going to stay on the bridge?
No. I was just trying to bring across the joke. Bridge, London, networking. Come on, Joe.
Drink more.
Yeah, my Guinness is empty, so the jokes are not getting better. Who in this room has ever saw how Neutron Networking works? Neutron Networking with OVS, it's actually fairly simple. The way was that, did I say something wrong? Neutron OVS is very easy and simple to set up. It always works, so when it doesn't work, it's your fault. Just configured it wrong. Also, the model, the model how you configure networking in Neutron, it's the best model we have. So there is not a single thing in Neutron that needs to be changed to make users more happy with it. Nonetheless, we decided for MeetUpNet, MeetUpNet is fully OpenStack Neutron compatible. So there's nothing in MeetUpNet that does not fit into the way Neutron understands how Neutron ports work with VMs, how networks work, how DHCP works, how tenant routers work. And one thing that you may not be used to is the concept of the provider router, which does not exist in Neutron. The provider router is a router. And MeetONet has two modes. The MeetONet, the normal MeetONet 1.9 needs a provider router. So you need to build, you basically have all your Neutron networks and all your external networks are sitting behind the provider router. In OVS, this is different. In OVS, the floating IPs of the VMs that are sitting on the external network are not sitting on the northbound side of the provider router because there, in general, Neutron OVS, there is no provider router. There's only layer 2, where you have your VMs. MeetONet uses a provider router to build a virtual router that is distributed across all MeetONet gateways responsible for handling your traffic using ECMP BGP. These were a lot of geeky nerd words for saying a simple thing like we can scale your traffic. We can use MeetONet gateways to scale out your traffic in terms of bandwidth and in terms of flows per second, so in terms of connections per second. And this includes all layer 3 connections and layer 4 load balancers, which is implemented by our gateways. The MeetONet gateways are basically machines that are having legs of the provider router. So you bind the northbound interfaces, the virtual parts of the provider router, you bind them to the MeetONet gateways. And in this way, we can move your traffic between the overlay and the physical world. In the case of tenant routers and networks, it works exactly the same as a Neutron. But in the physical world, you see the difference. MeetONet itself is based on agents. And the agents are little programs that sit on your hypervisors and on your MeetONet gateways. The gateways is something like a better version of the network node. So if the network node in OpenStack Neutron would have been designed properly, then a MeetONet gateway would be the result. Some good step in the right direction is DVR, where we actually have a good distributed way of sending traffic south-north and north-south. But DVR still is like about 40 to 50% of what we can provide as a commercial package, as a finished product that we call software. The MeetONet gateways basically have an agent, and everything is moved through the network using tunnels. So the VMs sitting on vPods will use a MeetONet agent to send their traffic. The way this works is OVS uses a program called, uses a kernel module called OVS data path. And the OVS data path can be programmed using netlink messages. So when packets arrive from the vPods of the VMs, normally the Open vSwitch userland components get netlink upcall messages that tell them that a new flow has arrived. And then the OVS component will install a kernel flow that tells the kernel what to do with this packet. It's coming in on a vPod from the VM. Now we replace the OVS userland component, but we do not replace the Open vSwitch data path kernel module. We will use this kernel module because it's actually very good. It's a very good piece of software. We will use this kernel module and let MeetONet agent create this flow information in the kernel. Because the MeetONet agent, as Joe once put it, has the perfect overview and the perfect knowledge about the whole overlay. Every MeetONet agent uses what we call the network state database, which is not in this picture because it would be very confusing. Every MeetONet agent learns the whole topology and can simulate the path of the packet through the virtual topology. For example, the VM wants to send. So it goes to the virtual switch, goes to the virtual router, goes to the virtual provider router, which is a combination of all network cards on all these gateways. And using BGP, the packet gets sent out to the internet. Now the reason why it scales is every agent does a local source-based decision, makes a local source-based decision that tells us which of the gateways are available, which of them are down and which are available I can use. So each gateway, each agent on the hypervisors can use any gateway for sending information, for sending packets to the internet, makes a local decision, source-based round robin, and uses a direct VXLAN tunnel going directly from the hypervisor to the gateway without jumping through a namespace, without jumping through IP tables, without going through a network node. So there's no bottleneck, or there's no second or intermediary step that you need to take for sending your traffic out of the cloud. And for traffic that goes into the cloud, it's the same thing. How are we on time? What's the time? No, that's not yet. That's not right. How much time do we have left?
I'm not sure when we kicked off.
Okay, so north to south, it's essentially the same thing. The gateways are running in ECMP, which means for every packet they receive, when the destination is a floating IP, the gateway, if it's a new flow, will send flow state to all the gateways in the pod group. A pod group is basically a federation of gateways to accept incoming packets for the IPs that the gateways can accept. And it will also send a flow state about the reverse flow to the hypervisor where the VM is sitting. So the packet comes in, the first packet, tunnel gets created, VM answers, and VM has already the flow state and can pick which gateway to send the return packet out to, and subsequent IP packets of the same connection. For example, if it's a TCP layer for load balancer, can go to different gateways into the cloud and to the VM. Does this make sense? No questions means you didn't understand it.
So
Yeah.
why do you, I mean, I think you're trying to preserve the layer 2 connectivity between your VMs.
The virtual layer 2
But
connectivity,
you
yes.
don't need layer 2 connectivity for going out to the internet. So
No.
For going out to the internet, why don't you just do BGP all the way to the hypervisors?
You mean like
and then
Contrail?
just use a normal BGP technique to route.
There's more than just that one use case for OpenStack.
It's a very good question. We could use, we could do the Contrail way. We could use layer 2 extensions for /48 BGP announcements. So that's basically what Contrail does. But then we would remove a lot of intelligence from our agent. And we have decided very early when our company was created that we want to get world domination by having an agent make all the decisions. So no BGP, no overlay routing. So in the overlay, you cannot actually route. If you want to do routing between your VMs, we don't care. But the overlay traffic itself is completely simulated in the agents. And the agents, they do not need BGP as a control plane. The distributed, we could think about having BGP as a distributed control plane, but our flow simulation is written in Java, and it kind of works different than BGP announcements, because to scale BGP very nice, as I said, it's a very interesting topic because the Contrail guys are very successful with layer 3, millions of VMs, iBGP route reflectors, all this stuff. It's a lot of fun. But then you hit layer 4, stateful NAT, stateful load balancing, stateful firewalls. You hit all this layer 4 stuff. And then you would need one round of flow simulation in the agent and another round of BGP announcements for this traffic. And then it's more efficient to do everything in the agent in the first place, instead of leaving the routing decision to iBGP in the overlay using multi-protocol extensions, and then do the second round or the second insertion where you say, okay, for service chaining, for load balancing, for firewalling at the edge, for pod group firewall, for pod-based firewall, I do another round in the flow simulator. You would basically double the amount of work. And because in the flow simulator we get routing for free, why should we use BGP? Because the flow simulator on the agent, he already knows where all the destinations are. He has a list of hosts, vPorts, the MACs behind these vPorts, and the IPs behind these vPorts. So he doesn't need to do the iBGP to do dynamic discovery. But as I said, it's a very interesting topic. The Contrail guys are talking to us about this all the time. Maybe someone in this room will build a better networking product with actually this idea. I would be very excited to see it. Okay, next. 10 minutes, great. We're good on time. So nobody understands this joke. You're the only one that gets this joke because nobody worked with VPC before, right? So as I said, Amazon was actually the first SDN company. When the Amazon cloud was created, compute was pretty much done. So everybody knew VMware, everybody knew KVM, and 2010 was an exciting year. Basically, Google and Amazon, they already knew how to solve compute. And the next big interesting problem was virtual private cloud. How to build, how to allow your customers to do routing and networking in their own confined space of their own virtualized infrastructure without interfering with others. And when the virtual private cloud was created, this included elastic load balancers, peering, VPC peering, security groups, firewalling. VPC was basically what made Amazon successful, because virtual machine hosting is very easy, but having networking, really cool networking, I think this is the reason why Amazon was so interesting to developers, because they could build their environments where in the past they had to go to a network administrator and beg them for VLANs. And I mean, everybody knows how that goes. No developer likes to wait for days for routing and VLANs and network ranges. So let's take a quick look at the age distribution in this room. Who gets this joke? I think nobody. Okay, I gotta work on my jokes, Joe. Nobody knows where this is from. Come on. Come on, Mark. Help me, please help me. Rescue me.
No, I can't see that either.
It's from Zack McCracken, which is a Commodore 64 computer game.
Oh.
None of you had a Commodore. You all had an. You had an Atari, right? All of you had an Atari. You're the Atari folks. So VPC router peering with Meetupvideo allows you to show you're very lazy. VPC router peering turns an OpenStack Meetupvideo system into a fully compatible VPC setup, where if you do not have VPC peering, then you can build an OpenStack cloud with tenants, and tenants need to use floating IPs to talk to each other and to talk to the outside world. With Meetupvideo VPC peering, like you can see here, you can build wonderful things. You can have tenants share routing with each other in the same cloud and different clouds. You can have an OpenStack cloud, and the tenants in this OpenStack cloud talk to Eucalyptus instances in a Eucalyptus cloud that runs Meetupvideo with VPC peering. So you can have a hybrid internal cloud. It's based on OpenStack and Eucalyptus, and you can share private routing between a Eucalyptus tenant, where users have their instances, and their VPC. And actually in Eucalyptus it was called VPC in the first place. Eucalyptus doesn't even have the concept of tenants. And an OpenStack cloud. And in the future, at the moment we are working on being API compatible to Amazon. In the future it will be possible to have router peering between any OpenStack cloud that you build with Meetupvideo and any Amazon VPC tenant that you have in the wonderful internet. And there's something our customers have been asking us for 2 to 3 years now, and finally we got around to build it. Last year I wasn't able to present it because it was already in the works. But with Meetupvideo 5.0, it actually came out as part of the enterprise product. It will also be in the open source product, so far as I remember, right?
Yes.
Will also be in the open source product. So Meetupvideo comes in 2 products. Sorry, go ahead. 1 minute.
That was 5 minutes.
5 minutes, okay. So, like I said, Meetupvideo comes in 2 products, an open source version and an enterprise version. The only difference is that if something fails in the open source version, you need to go to the open source channels and to the open source community. We have a forum and a chat bug tracker, and you can ask there for help. And if our developers are bored, then they help you. Most of the time, they are not bored because they're busy helping the paying enterprise customers. So that's basically how it works. The concept is the same like Meetonet. We have a so-called virtual tunnel endpoint router, a VTAP router. VTAP is a concept from the switches where with a VTAP switch, you can have physical networks connected to an overlay. And we were so fascinated by this concept that we have built a virtual tunnel endpoint in software, and we put it into Meetonet. And this software allows us to set routes to the other tenant in our own tenant. And these routes are used to send traffic to each other. So whenever a VM sends a packet to this other VM, then the following happens. The black tunnel is the tunnel between the hypervisor agent and the gateway agent. Now, inside this tunnel is the VTAP tunnel, the router peering tunnel, that is used to send the traffic out to the internet. Does this make sense, Joe?
Yes.
Okay. Now, the next optimization was, because double encapsulation is pretty stupid and we are all grown-ups, the next optimization was to have the encapsulation actually not be double encapsulation, but to have the encapsulation only begin at the Meetup gateway. So our developers, they optimized it and said, use one tunnel to send it to the gateway, and on the gateway, just create another tunnel. Does that make sense, Joe?
Yes, please.
And then from gateway to gateway, and the gateway is part of the provider router. So after the gateway receives it, the next gateway in another cloud, then just build another tunnel to the hypervisor where the VM is. So basically, you have 3 tunnels. From hypervisor to gateway, from gateway to gateway. This can be anything. This can be Eucalyptus or Amazon, or another OpenStack cloud, or it can be the same OpenStack cloud. And then from the gateway back to the hypervisor. If it's the same OpenStack cloud, it's actually optimized that it's only a tunnel from hypervisor to hypervisor. We don't need to invoke a gateway to send it back to the gateway again. Software is not that stupid. And then another optimization is normally, for security purposes, you would be doing VXLAN tunnels, router peering starting from the gateways. It's a very secure setup because the traffic is not moving through your fabric, through your corporate network. But some customers, for example, public cloud providers, they don't care about data center corporate network security. They just don't care. They have a big cloud network, data center network for their public cloud. They just don't care what happens with the tunnels. So they are actually start the VXLAN tunnels on the hypervisor, send them out to the other cloud in the other data center, which is super, super fast. Because the only thing that is basically, the traffic does not even have to pass the gateway. Means no network I/O, no network bandwidth is used. You can off-ramp directly locally, and this resembles a lot DVR. It's basically DVR with router peering. Thank you. Thanks.